Yeah, we're good to go.
Okay.
Yeah. So I'll say 2 words and then you'll say. So let me just say 2 words just as like a, so good morning and welcome to the Medgar Evers College Math Department Colloquium series. I wanted to say a few words just as a kind of background. Zach, who I'm meeting today for the first time in person, Zach and I worked on this paper for almost, 2 years?
Yeah.
For about 2 years. And so we've had this long ongoing relationship. We've done talks together at the joint meetings via Zoom. We've done sort of talk for the folks in Portugal via Zoom. So I just wanted to say thank you to Zach and to say, welcome to Medgar Evers College, and we're quite happy to have you here. And then to, our department, we're in a kind of rebuilding mode, and I think that the most important is mathematics. We're a mathematics department, and so while we're challenged with managing the mission of the college to integrate sort of communities that have been underrepresented in mathematics, the operative word here is integrating into the world of mathematics. That's the tool that we have some expertise in, and so I just want us to always keep that in mind, that part of what we're trying to do is to grow a culture of mathematics here at Medgar Evers College. And in that respect, I want to thank you all for the work that you've done this semester, and just to say that I have 2 bottles of wine in my office, so after this we will have a little bit of we'll infuse the math talk with a little bit of the Christmas spirit. So having said that, I'll turn things over to Josh and he'll introduce you and we'll go on our way. Josh.
Okay. Thanks everybody for coming. So today's speaker is Zachary Stier from Berkeley, who will tell us about optimal topological generators for the circle.
Thanks for the introduction. Thank you, Josh and Terrence, for having me here, and it's an honor to speak to you all. So my name is Zach. I'm going to be speaking about this topic, and please do stop me at any time and ask questions if there's anything at all unclear. So here's the broad outline of what I'll be talking about. And first I'm just going to start with some pictures. So here is the general problem. We're taking a circle. Hopefully it comes out clearly enough. Maybe in retrospect it was a mistake to make it like yellow on the white side. But we've got this circle, and we're going to say it has length 1 instead of 2 pi. Just the one will be a little clearer once we sort of move to algebra and symbols and away from pictures. But we're going to take this circle of length 1. We're going to start with angle 0, and we're going to go out by some angle, and we're going to mark off that point. And then what we're going to do is we're going to mark off the next multiple. So the way I think about this is we went all the way around by this amount, and then the same amount around here. And I've deliberately chosen a pretty large angle, so we get kind of chaotic looking behavior. So the next multiple is like this, this. And I've done my rudimentary best to simulate a video or a GIF inside this presentation. So hopefully this works. So maybe I'll start from the beginning. So hopefully that had the right effect. So what is happening is we're taking all these multiples and we're filling out the circles. So keep going. And these numbers are just to give me some runway so that when I run the video, I can know when to stop. So these multiples. And maybe it's a coincidence, maybe it's not, that I've chosen an angle that it actually looks like these are pretty well spaced. And this whole talk is really going to be about quantifying what that means and seeing what we can prove about this. So if we do this exact same procedure, but instead we mark off all the different lengths that we get, then we'll actually get some very interesting behavior. So to start, we only have two different lengths. We've got sort of the long way and the short way. And then when we do this again, we've got two of these long ones and one short one. And it continues. And now the color scheme changed. So I was using orange and black to mean that we only have two different lengths, and then red, blue, green to mean that we have three different lengths. And so always in these images, red is going to be long, blue is going to be medium, green is going to be short. And we keep going like this, and like this, and like this, and like this, and like this. And maybe you'll notice that I never actually moved up to 4 colors, which is kind of curious. And also, if we sort of go out kind of far, maybe to the very, very end of this sequence here, I'd say that these are actually pretty even as far as our red, our long, looks to be about twice as long as our green. But it's not too bad, I'd say. And so we're going to see what we can actually prove about this. Okay. So as I said before, we've got sort of the circle of length, the total angle 1, and we've got this irrational angle. So we're going to specify irrational because irrational, a space irrational angle is not so interesting, right? We just take multiples, and once we've taken denominator many multiples, we're back at 1 because everything's mod 1. So the only interesting thing that happens is irrational, because a rational one would not actually be dense, right? We're not going to fill up S1 because we're going to have all these gaps. We're going to end up in the same number of slots, same denominator, many slots. And there's this theorem, I've never really seen it proof written down, but the kind of, I think, amazing fact is this thing that we're observing empirically for these first 50 multiples was that we're never going to get more than 3 different lengths. I think that's very surprising, but I think it's something that is possible to convince yourself of if you just kind of imagine, well, we've got these multiples going out, and then when it wraps around, it has to sort of be a shifted version of the thing that just happened, and by the time you end up with a fourth, you've kind of deleted, you've already interrupted. You only got one copy of your smallest length, of your least common length, and then that gets interrupted. So that's kind of the behavior that happens. So this is an interesting fact. And then what we're really going to be after is no theta can generate our circle too well. And put that in quotes, because what does that mean? And we're going to mean it in this sense. So I'm going to say d theta of m is the longest resulting arc. So it was the red, generically in the case before, or the orange, when we only had 2 different ones.
Sorry. So when you say that the way you're doing is you're taking one point and the next iteration, and that's what you're measuring, right? And that's red or green. And there's only 3 possibilities.
So what I'm doing is, so even though from, say, this one, so our last point was up here, and we're going from here all the way around to down there, say, we're then measuring, instead of the order in which we wrote them out, we're sorting them essentially. So we're taking our multiples, and
so that's the previous iteration, just like the next one.
Yes. The next one, when you go around the circle, not the previous iteration.
Okay. Exactly. And there's only 3 of those distances.
Exactly. And this is, because if we were just tracking one multiple to the next, it would just be the same length every time. Right? But there's this weird behavior because of the wraparound, because everything exists mod 1. So that's what d theta is capturing. It's when we mark these off on the circle and allow for the wraparound, what's the longest resulting arc? And so this is always going to be bigger than 1, right? Because we've got all these arcs, we've got exactly m arcs. And the longest one, if you sort of replicate it out m times, is at least as big as every other arc. But the total sum of those arcs has to be 1, because we started, they just are partition of the circle. And so their total has to be 1, so this has to be at least 1. And if we had some magical number that always marked off exactly equal intervals, this would be inequality. we can't get inequality, we can actually quantify the extent of the failure. So we're going to fix theta. Theta is not going to change through this, and we're just going to look at, for a very, very large n, what does this quantity look like? It's going to be bigger than 1, certainly. And it's always going to be at least this big. So we'd hope, okay, for this magical number, we can hit 1, and we're saying no. The best we can do is 1.9 or so. And we can also say exactly when this quality happens. And I'll define what this notation means in a little bit. But this is not a theorem. This is a theorem of Graham and Van Lent from the 60s. And they are able to do this with some very nice continued fractions work. And that's sort of what the vocal talk is going to be about. If you turn this problem into a problem of continued fractions, then you can actually answer these questions, which I think is quite nice. It's a very beautiful theory of continued fractions, and I think it's very surprising that they're able to answer these kinds of circle geometry problems, if you will. So that's, I think, this really cool theorem of Graham and Van Lent. So I'll make sure this is clear that sort of for very, very large n, you can always find a larger n, so some very large n, such that this quantity is about 1.9. And so sort of your failure to equally space is at least by a factor of 1.9. All right, so in order to talk about the proofs of the theorems that we're going to have here, we just need to set up continued fractions. So every rational number has this infinite continued fraction. So you can also write out continued fraction for a rational number. It will be finite, and there's a correlation between if you have a finite continued fraction, then you have a rational number, and sort of the inverse converse is true. So these are equivalent: finite and rational versus infinite and irrational. And the way you find this is you take your theta, maybe it's a number bigger than 1, maybe it's not, but you take the integer part, and then you take the fractional part, which is going to be captured by the 1 over everything else. Sorry, I should specify that all these a's are integers. These are all positive integers. Or this one can be 0, and then the others have to be positive. And then we've got the fractional part. In the fractional part, we just invert it and then do the continued fraction process. So we look at the integer part and then iterate. So it's there's sort of a symmetry to it. And it's kind of an elegant procedure. And so we'll see an example of it. But if we sort of truncate it and say, okay, what are the rational approximations? Because as you go further down, the nth value in your continued fraction, the nth coefficient in your continued fraction, won't impact it that much. It doesn't really matter if the 100th number in your continued fraction is 1,000 versus 1,001, for instance. That's not going to change the value very materially. So we can think of these things as actually converging to theta. And so this is why we call it the convergence rate. They actually do converge in a proper sense. And so if we chop it off, we'll say, okay, h over k is the number value, and they satisfy this very nice recursion. So it's actually, this is, the top line and the bottom line are equal because of some nice coprimality results, which is actually kind of beautiful that we don't get any cancellation, that these are actual, like, this is recursion, this is recursion, there's no constants that are being omitted here or canceled out. So as an example, if we just have all ones, so ones all the way down, we're going to call this 1 dot, just to sort of save us some space. And so 1 dot, just anytime we see it at the end of the continued fractions, we just do all the ones. And we can evaluate this to be 1 plus root 5 all over 2. And there's a very nice proof of this, actually quite elegant. It's that you call this, this is going to be phi. Phi is defined this way, so call this phi. So maybe I'll break this. So we have phi is like this, because we're just able to replace a 1, 1, 1, 1, 1, 1 with phi itself. Because phi can define to be 1 dot, which is equal to 1 comma 1 dot. And this is 1 plus 1 over phi. And then you solve for phi, quadratic formula for however you like, and you come up with this number. and it's about 1.62. And we can check through this recursion that these convergents are actually just Fibonacci numbers. And in fact, if we see, well, our ANs are always just 1. So HN is the sum of the previous two HNs, KN is the sum of the previous two KNs. It has better be in the Fibonacci numbers. So that's really nice. And we're then able to recover the sort of classical Fibonacci result that the limit of the quotients of successive Fibonacci's is exactly the Golden ratio. Which is also, goes under many guises. This comes from Binet's formula. But this is kind of a quick conceptualization of Fn over Fn minus 1 limits to the Golden ratio. There's also other very cool things you can say about these convergence. We won't need this fact, but it will just share one really cool fact that I highlight, is that the even ones approach theta from above and the odds from below, I think, or maybe vice versa. But sort of the alternate being above, below, above, below, above, below, which is very nice, very elegant. So that's the first setup of two fractions. And now I'm just going to introduce a little more notation. So from theta, we can introduce xn, which is just we take the first n plus 1 of these a's. We're going to throw away a0. Just because a0 is sort of, we care about things mod 1. And so if we take theta mod 1, a0 doesn't matter. All that matters is remaining a's. And so we're going to reverse it. And it's a kind of cool fact, actually, that it's equal to the quotient of these successive denominators. The proof, I think, is just, you can just induct on this proof. And then theta n is we're just going to take theta and chop off the first n. So we're going to start with an and go down. And so there's also some nice recursions there, like we can write the theta in terms of theta n's. But these are just more, they're just concepts here, more just notation that's going to show up later on. This other thing, so this is a sort of equivalent notation that I mentioned a couple slides ago. That was another fun. So all we're saying is mu and sigma, if we can chop off some prefixes of them, possibly of different elements, and we recover the same continued fraction, then we're going to say a variable. And so maybe a nice example of this, or a core example is we have all ones and then 1, 2, all ones. We would just chop off this prefix. Then these are the same continued fraction.
It's like an equivalence class. So.
This is an equivalence class of real numbers given by the continued fractions. Or maybe we can make an equivalence class on real numbers because the rational numbers will just have zeros all of them. So this gives us our equivalence classes, and our equivalence classes show up in that theorem, which is kind of amazing.
Sorry, so for phi, how many elements are in the equivalence class? Is it?
It is going to be countably many. Yeah, because so each equivalence class will have countable size. Because all that matters is you've got prefix a0. Right. And this sort of our number of choices is natural. And we do this for each level. And so we get a countable partition.
Before you define that, I assume that phi and its conjugate would be in the same equivalence class, but it's not. It's something. I mean, because the conjugate would be negative, so it's probably not.
No, actually, phi and its conjugate would be. So, okay, actually, I guess when I said that this allowed to be 0, we can also make that be negative.
Okay.
Yeah. Really, what's going to be important here is for like this first one is it gives us an angle, and we can think of it as going rocking around negative times the fruit instead of positive. And then the last thing is we're just running. This is a number 1 over 1 plus 2 over root 5 that showed up in that theorem of Graham and Van Lent. I just want to give it a name. It's nothing really special about the name. I just wanted to have a name for it. And now we're going to be able to set up some of these facts that are going to be useful for both proving the result of theorem of limit and then the theorem that we're going to have subsequently. So if you combine some results of Slater and Soch, and also, so Harding Wright is just they've got a beautifully written chapter on P fractions in their book. I think it's Intro to Theory of Numbers. And it's a wonderful chapter that has some incredible theorems. I think there's nothing too fancy from that chapter that goes in here. Is just sort of nice computational simplifications that we're able to do. But what's important is that we can say, okay, pick a constant alpha. It's going to depend on an. And then if we pick little n, and our alpha depending on little n, and then little m, a whole number, to be parametrized by these convergent denominators, by these k's, then we can actually write down exactly what d theta is. And you'll see that there's no m's in here. We've got two different forms of this expression, but there's no m's. So this number is constant across all n's inside this interval. And that's kind of the core mechanism that lets all these proofs go through. That through this Slater and Soch machinery, we're able to say d theta is precisely this and depends only on n, doesn't depend on m at all. And so using this, Jeff Mazzocchi a few years ago was able to show the following. I was able to show that on such an interval, so here we're going to pick alpha to be 0, which of course we can always do because an plus 2 is always at least 1, it's always a non-negative factor. We're going to start with theta, which is in this equivalence class of phi. And we're going to say that this starts to be true after n. Well, then we can actually say exactly what this, on this whole interval, what m d theta of m is. And of course, m d theta of m is actually constant on this interval, but the max is going to show up in a little bit. And so this is conceptually very nice, right? It's a quotient of things. We have these x's, but that's okay. These x's eventually are going to look like, all ones to start. But the point is that it's just a nice quotient. It only has 6 terms in it, which is very convenient. And so using the first of those results, so using this lemma, the top thing, we're able to prove Theorem van Lent's theorem. And I'm going to skip over the algebra because the algebra is not the most annoying. It's really the idea of how to use that result. So we're using the case alpha is 0, and we're saying that this lim sup of m d theta of m is at least, well, we know what m d theta of m is at least this. So we're just sticking in this inequality inside the argument of the lim sup. And then we transform here to here using continued fraction algebra. And then we just do a little bit of case work. So notice that top line to bottom line, try to double it, right? Or try to double bottom to top. So if theta n plus 2, this theta term, is always bigger than 2, or at least 2, then this whole quotient is at least 2. And this is happening a lot. Then the lim sup will also be at least 2. Could be bigger following, but certainly it will be at least 2. And recall that our sort of target value, our rho, is 1.89. Right, it's smaller than 2. So we're saying if this thing happens, then this is going to be at least 2. But theta n plus 2 being at least 2 just means that, recall that the theta n plus 2 begins with an, or an plus 2. Right, so this being at least 2 means that an plus 2 is at least 2. So in order to have this lim sup drop below 2, we're going to need to have theta n plus 2 be smaller than 2 always. So this being greater than 2 can only happen finally off. We want this to be smaller than 2 eventually. And so these an plus 2's have variably 1. But if our an plus 2's are always 1 eventually, we're in the case of equivalent to phi.
That's not the proof that Graham Van Lint originally had.
This is a proof.
Oh, but is this the proof?
This is their proof. So this doesn't use Mazzocchi's stuff. This only uses, Hardy Wright is much older, and they cite Slater-Soch extensively. This is Graham Van Lint's proof. And I think it kind of gives us an idea of how to work with, sort of how to transform into convergence and work with these convergence in these ways. So now I'm going to talk about a sort of proposition about what are good generators and what they means. So suppose we're starting with, again, something in the equivalence class, because this is already what we want. This is a set of fractions, PG fractions with good lim sups. Well, when does it reach row from below? So I've marked off in green the line row. And I'm plotting here md theta of m for each m. So this is the m axis, this is the md theta of m axis, and this is just totally out of control. I don't look at this and see any structure here. But I did choose thetas which are in this equivalence class. So the question is, can we characterize them that approach from below? Or in other words, is there this lower bound m theta for which, after that point, the md theta m's are stay below, and they never do this wild behavior of popping above, or maybe popping way above, as we see for the second one. And the answer is yes. So we're actually going to be able to show that for all of these thetas, there does exist this m theta that makes this happen. And if you really want, we can compute an upper bound on m theta. It's going to be large, but we could say that it is. It'll be kind of indirect from what's written here.
This is your theorem?
This is a result in my paper about this. So what we're going to do is we're going to say go beyond n by d. And as is suggested by this Hardy-Wright-Slater-Soch lemma, we're going to pick n between these two numbers to be in this interval. And so we're going to have, of course, that this is the case. This being from Jeff Mazzocchi's paper. And so, well, md theta of m is at most the max, is at most the row. If the whole algebraic condition is just going to come down to this. And sort of, I know I really black box something to go from this to this, but all that's happened is we use the sort of lower bounds on kn, on k little m, and compare these against sort of the last convergence that we have, and I've just sort of omitted some out. The algebra again isn't especially enlightening. I really just want to give the idea of these are the observations we make. We do some algebra, we come up with this, and then the crucial part is that n is fixed, d is not. So we just need to pick a little d such that the Fibonacci number, the d plus first one, is at least this number. There's eventually one big enough because this number is fixed. This depends only on theta. We get to choose this. We get to choose however far out of it we want. And so that's how we can compute m theta. All we need is to ensure that f of d plus 1 is at least this, and because we're given theta, we can compute m theta depending on when this happens. And that's the whole thing. And so sort of maybe one important observation is that this quotient here, again, we've got this 2 versus this 1 of this xn term, and the rest is just comparing sort of the extent of this quotient. So we see already to sort of first order, it's going to be about 2, and then how can we enforce that actually drops below this 1.9, which is about what rho is. So that is this whole theorem. And again, I've omitted some details, but I think none of the core ideas of the proof. Maybe core ideas of the proof earlier. So actually that is full characterization of these good ones, where good means it eventually dips below this row threshold. Right. So now we're going to move on to quantifying what the best ones are. So the best ones are going to completely bypass. We want to start from below. So Sarnak conjecture, the golden ratio does this. So notice instead of theta, we've got golden ratio here. This is a conjecture of Sarnak's, and Jeff Mazzocchi proved it in 2019. But the question is, what are the other ones? Are there other ones, first of all? And can we write them down? And the answer is yes, actually. So this is the other main theorem in my paper about this, that these are all. So this one is a golden ratio. So notice that this up to negative sign and up to shifting by a whole number is a golden ratio, because this number is 2 minus the golden ratio. So there are 8, and I say distinct because I want to sort of draw the distinction between these generators and sort of the further equivalence class of the same up to shifting by a whole number and up to a sign, right? Because we get the exact same behavior if we go by theta or minus theta. And we just have the whole picture and it's going to be flipped. But since we're just flipping the whole picture, we're not, the behavior itself is not any more or less interesting. So that's really why I've omitted the 0 column, right? The A0 column. This is A1, 2, 3, 4, 5. And notice that 5, it's all 1s all the way down. And this is why I call it 8 instead of 16. So each of these has a sort of companion, which is its
So in a sense, you have like an extension of Sarnak's sort of golden mean. These are new Sarnak golden means, so to speak.
Exactly. Yeah, because the Sarnak conjecture here's a specific number and then asks what are the others, and so this provides an answer.
So this is a full classification.
This is a full classification. There are no others.
And what is the enumeration on the left? What applies to A to 1, A to 2, label like this?
I believe they are increasing in numerical value of the smallest representative in the interval 0. And then, so that's what this subscript is, and then these are sorted lexicographically. So first in the 1 column, then within that in the 2 column, then as necessary.
Am I jumping ahead? But what sort of general implications to be drawn in this sense?
Sorry, in the sense of the
in the sense of that you have more of these things than sort of originally envisaged.
Yes. I don't really know exactly what interpretation. Actually, there might be some interpretations. Maybe I'll get to that after we prove the theory. Yeah, I think there's a sign that I think we can address that there. So just sort of want to eyeball it. These are A to 1, A to 2, and this is what they look like. And indeed, it appears that they are all below this row number. Obviously, it's not a proof. I just made my computer do this and it spat out this picture. That's not a proof. But certainly it's very convincing that, okay, it's clearly approaching from below. It could drop, dip above. But I'm going to claim and I'm going to prove that they do. And we can also eyeball it in this way. So we take more of these circle diagrams, right? So I think this is out to 75 iterates. And I have these 8 etas and then pi. Pi I chose randomly as a non-number. Pi has a non-repeating, very chaotic continued fraction. And we can look at how nice and evenly spaced this one is, and that one is, and that one is. And look at pi with all these very long intervals, and then all these bunched up green ones, these long blues and these long reds. And I think this is kind of telling of maybe if we spend too much time staring at eta 6 and how nice and evenly spaced it is, we can forget that the generic behavior of the real numbers is much worse, much worse. And pi kind of witnesses this. And you'll get the same behavior if you choose E or almost any other real number. So.
It means there can be like obviously, so phi is algebraic. Is there going to be, if you choose other algebraic numbers, I know phi is really good, but is there going to be a difference between transcendental and algebraic choices?
I think the difference is going to be with respect to whether or not it's a quadratic surd.
Quadratic surd.
Surd. So whether it's continued fraction repeats or not. So actually, this is one of the really cool proofs in Hagen-Wright, that the ones with continued fractions, with repeating continued fractions, or eventually periodic continued fractions, maybe with some prefix, are exactly the ones that are roots of quadratic equations. I guess non-trivial roots, obviously integers can be roots of quadratic equations. But beyond that, the sort of after these 8, or after these, the equivalence class of B, the nicest ones are probably going to be the ones with just repeating continued fractions. So we're going to prove this theorem in 2 steps. Again, I'm going to sort of elide over the messy algebra and sort of showcase the nice clean expressions. So what we're going to do is say an is the last one that's bigger than 1, the last continued fraction coefficient that's bigger than 1. We want to show that we never have to go further than 6. And actually, if we look back to our table, we never need to go beyond, an equals 3 suffices. But we're going to be able to show algebraically that it's actually 6, or that we can show algebraically 6. And then a computer search reveals that it's really 3. But no way to really know this coming into the proof. No way to know this. We're sort of approaching it without that foreknowledge. And so, using Rm and using m depending on Kn, we're able to show that for this m. You can exactly write down m and theta of m using, again, our Slater social. And the condition that this expression is smaller than rho, after sort of rearranging as this, theta m plus 1 is just Coulomb ratio, and all sorts of nice simplifications, we come out with this means smaller than rho is equivalent to this. Just algebraically, you can recover this from that. But now look at this. This number, these are all positive. The 2 minus rows are positive as well. It's like 0.11 or so. This is at least 2. So this we can lower bound. This we can lower bound. So when Kn and K minus 1 are a certain amount large, this ceases to hold. But we have lower bounds on how fast these Kns grow. They grow as Fibonacci, or they grow at least as big as the Fibonacci's. So when n is at least 6, this has to be violated. The Kns have to have grown fast enough to violate this sum being smaller than 1. So we know right now that for a number to have, for theta to be in the class S of our friends in continued fractions that always stay below rho, this n number, this capital N, has to be n plus 6. Sorry, it has to be strictly smaller than 6. So now we're going to find some necessary conditions to hopefully reduce to a reasonable computer search. So what we're going to do is we're going to say for each of these coefficients, a1, 2, 3, 4, 5, we're going to look at m lying in this interval, the interval that we always keep coming back to, and write down our m theta of m. And this manipulates to just an is bound by this. First off, we're going to have smaller than rho. Is going to manipulate to this. Or again, we're going to use the fact that these Kns grow super Fibonacci. And this is just more sort of bounding, pushing the algebra around. But if we just plug in n equals 1, 2, 3, 4, 5, these numbers become these numbers. And none of these numbers are actually all that big. Right? In particular, we know that a1, 2, 3, 4, 5 are all integers, positive integers. Start at 1, end at 18, 18, 14, 12, 11. So the total number of numbers that we need to check is about 600,000. Not a terribly large number. Like, you know, computers these days can handle that in a heartbeat. I think I ran the code, it took like a minute. Not a very long time. So for each of these Slater-Soch intervals, we just do the same scheme of little m plus d, and then turns out we only check up to 29. The reason we need to do that is the worst case convergent growth, or denominator growth for the conversion, is for this number, this candidate. And it turns out that for this number, k6 plus k5 over 5 plus 205 is about f25. If you want to put Fibonacci. There's going to be some d that made this work. It turns out 24 is the one that works, just the way the numerics came out. And so by reducing down to the Slater-Soch argument, or the Slater-Soch reduction, we'll call it, where it was like, okay, we have a finite amount of work to do for each candidate, for each of the 600,000 candidates, and we just check all 25 or 29 of these intervals. And we know what's there, so it's afterwards we're set.
This is a weird question. So nothing has slipped your neck here? No. Okay.
Nope. And it's a Slater-Soch that allows us to conclude, okay, we only need to go up to 29, and we haven't missed anything by that analysis. And that's it, that's proof. So we just ask the computer, check all of these were at most 18, at most 18, 14, 12, 11. And then from there, we say, well, which ones pass the test? And it's the 8 of those. Or the 16 is, it doesn't know about the whole symmetry thing, but that's what it spits out. And so we can now ask all sorts of heuristics, numerics about this. So here I've alluded to Chebyshev and Littlewood. So these are two different sort of lines of inquiry. So Chebyshev is a reference to Chebyshev's bias, which is this very strange phenomenon where I don't know what the elementary proofs are, but like Chebotarev density, for example, tells us that primes which are 1 mod 4 and 3 mod 4, asymptotically there's about the same number of each. But if you plot, you just count for really large n, like number of primes that are 1 mod 4 and 3 mod 4 up to n for really large n, there's more that are 3 mod 4 than 1 mod 4, it seems. And this is a result of Sarnak and Rubinstein in the 90s, that this always happens, that there's always more primes that are 3 mod 4 than 1 mod 4, even though asymptotically they're the same. On the other hand, Littlewood has this striking result that if you compare the prime counting function, so how many primes are there up to n, against the logarithmic integral of, it's the integral of 1 over log x from x equals 1 to n. It's been known since like the 19th century that these are asymptotically the same. And people had done sort of the numerics of how do these compare absolutely. And they found that, I think, the prime counting function was always slightly larger. And it was conjectured it was always larger. Littlewood, and I think the 19-teens or so, proved actually they alternate. And I don't know if he established that they alternate, but there's this now like minor cottage industry of establishing when is the first alternation point. And the first alternation point is believed to be something like this. So number of primes at most, this number is the first time that it drops below the logarithmic interval. And it's actually known that there are an infinite number of alternations, that they keep one-upping each other eventually. But no one in 1910 was going to know, could have checked this far out. We still can't check this far out. And yet Littlewood was able to say, no, it happens and it happens at 10 to the 300,000 or whatever absurd number. I might be misremembering, but something like that.
Does the alternation happen in a regular way, or?
I don't know, but I suspect not, or at the very least, I suspect that we don't yet know enough to establish. Because, you know, the improvements on this, I think the true number actually is maybe like 10 to the 365, and then improvements are like improving it to 10 to the 362. Something like that. So these are, you know, minute improvements in the exponent, but the quotient between these numbers is just so massive that I don't know if there's any nice regularity in them. So we can ask kind of similar questions of, well, does one of these 8 numbers do much, much better than the others, asymptotically? Long-term, short-term, what can we say? So if we call Wn the theta, which does best, has the smallest maximum across 1 through the input, capital M, does each theta rise infinitely often? And the answer is yes. Each one appears at least as the best one with probability 2.7%. Some of them are much more popular, but the least popular one, the least asymptotically good one, is good with probability 2.7%, which is, it's constant size. That's not vanishing. And that's like, it has a real piece of the pie, if you will. So I'm not going to talk about the proof of this just because I'm not, conceptually this proof isn't as nice. It's mostly pushing around convergence and unenlightening algebra. Algebra that's, I think, not very fun to think about. But I think it's a kind of punchy result, kind of nice way to tie this together. And if try to eyeball it, we'll see that eventually, like, if we look at red, or okay, maybe the red in, there's a couple different reds in here. But like this one gets really high and then drops off, and so stops being really bad. High up is really bad. So this one becomes the worst one, and then becomes really good. And so by the time we're over here, red is pretty good. And red's been overtaken by blue, so blue is much worse than red by here. And this sort of Littlewood type behavior of each of the thetas being really good until it shoots up and becomes bad again, and then slowly becomes better, and then shoots up and becomes bad, and then sort of tapers off. It was the inverse of, you know, slowly creeping up and then shooting down, just because we're sort of looking at different angles of it. I think, even though this, I know this is an eyesore, and I know this is kind of like disconcerting to look at, but that's kind of the way I read this graph. So I think it's kind of neat in that way. And so we talk about an idealized application. And so maybe you all have heard of this pop math fact of like the Fibonacci numbers show up in nature all the time. And how many leaves do sunflowers have, and how do their leaves grow, and how many petals do they have, that kind of thing. I think even this, you know, cartoon drawing, I think it's kind of clear that what's happening is that this is golden ratio multiples, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like these are the golden ratio multiples. And so the pop math fact is that the leaves of a sunflower, to maximize sunlight, to maximize the space around that they get around them, so that they can take the biggest share of sunlight, grow at golden ratio angles. And now we kind of have a proof of this, right? If we look at what are the, which are the ones that achieve WM, so which are the best ones, I color-coded them, and I think the golden ratio is the black ones, so these are the leaves. So if you believe that your sunflower plant is going to grow about 10 leaves or about 30 leaves, then in fact, golden ratio truly is the best one across all numbers, and we can quantify that. We now have a rigorous way to say the golden ratio is the best angle for your leaves to grow. Here's how. Now, if you think your sunflower, maybe your sunflower doesn't know how many leaves it's going to grow, of course. But if it did, if it typically grew between 20 and 30, then maybe the golden ratio isn't exactly the best. Maybe it's whichever one corresponds to yellow or light blue. But the point is that there's a reasonable interpretation to what each of these 8 numbers means. And hopefully, Terrence, this kind of addresses your question from earlier about one way to interpret this. Obviously, this is super duper idealized, and this is not how nature works. But it's not too terrible an approximation, I think. So now I want to just close out by talking about briefly what happens in hybrid methods. And this is going to be where quantum computing enter. So this is not going to directly relate to quantum computing, but we have talked about the circle so far, which is the first unitary group. We can say, what about other continuous groups? The unitary group has a circle, we have a circle metric, but we can do other continuous groups, often Lie groups. And so we're going to talk about a group. We're going to pick a generating set, and it's going to be a finite generating set. So it can't densely generate, but we're going to look at words of length up to n, and we're going to hope that they're dense, and we're going to say assert that they're dense. And we're going to say, what is the largest epsilon ball? We've got this metric, we've got centered around G, this epsilon ball, that doesn't meet a set, that doesn't meet our words of length up to n. And that's what we've been studying this entire time in different languages. We've been studying this for G equals U1 and S a single number, a single irrational generator. And that's exactly what we've been thinking about. The largest empty space, the largest open interval, the largest ball, because an interval in one dimension is a ball. We also answer for S2. So S2 we use different machinery. But we can actually relate to quantum computers as a motivation and say, okay, well, we've got n qubits, and we turn to a hardware design problem. And we want to say, for a target, a gate is what we think about as. How far out do we need to go? And for n equals 1, so for 2 to the n, and this is a solid Kitaev theorem, which is a sort of classic result of quantum computing. And it's actually a result of Terrence and mine that this can be improved almost everywhere to, there should be a log base 59 in here. Yeah, 59 is arcane and opaque where it's coming from. But the point is that we get this logarithmic dependence and we can fine tune the coefficient in front. And now it's kind of open how to improve beyond 7.
So is your innovation that is the 7 important, or the base of the logarithm is important?
Our innovation is the application of getting the 7 to the continuous 7. So the 7 number was known in the discrete setting in the context of path finding in Ramanujan graphs, or in LPX graphs to be exact. And the demonstration is that, well, you can do approximately the same factorization that they use continuously. This requires sort of its own technical hurdles, but that's sort of the main observation, and then that's where 7 comes from, and then the 59 comes from the structure of the generator sets of the golden keys. And so that's everything I have to say. So this is a partial bibliography. So if you look at like this paper, they should have the full set of references that are relevant to this one. And I think that's it. Yeah.
Thank you.
All right. Please welcome.
Questions for Zach?
So is there some thought about what happens with other groups beyond this, you know?
Yes. So this is relatively open. Ideally, we'll understand PUPM. I don't think anyone has any ideas at the moment, or if they do, they're very much in their infancy. PU3 has some progress, but the difficulty, I think, is in setting up the correct sort of corresponding combinatorial objects. So as I very briefly mentioned, the 7 regime comes from the observation that you can do very nice things with Ramanujan graphs and LPS graphs. And for PU3, they set up something called Ramanujan complexes, which I don't know much about, but they're they're some simplicial complex that generalizes the Ramanujan graph. And then you need to actually understand these for the appropriate dimension, for the dimension that you choose. And I think this is quite difficult and not as well understood, I think, as people think. But that's the beyond SU2 setting.
Other questions for Zach? Second again.
So now that we're done, the one thing I was trying to think about there is this, to describe a bit the optimality, like the notion of optimality in the context of the circle, and then how to translate out that notion of optimality.
Right. So this is the optimality, I believe, is in the sense of covering exponent, is what Sarnak calls it. So the covering exponent is sort of, not exactly, or actually no, I think it is. It's, maybe I'll try to draw a picture. Capture this. So if we've got, so this is maybe our SU2 or PU2 or something. This is a manifold with 3 real dimensions. And we've got, it's covered by these points, by this S up to N is what is these dots I've drawn. And we're interested in what's the biggest ball we can fit that doesn't touch any of these. It's going to have radius epsilon. I think the covering exponent is something like epsilon is going to be eventually up to constants 1 over n to the k, or ks, where ks is, so what we know about Golombiers is that it's like this, it's between 4/3 and 2. And I think it's believed that you can never beat 4/3. And I don't know actually even if this is proved. And to compute this is quite difficult. So this is done out in Sarnak's letter. So this is a letter to Aronson and Holland. And this is, I think, the way in which we want to think about optimality is what, in terms of n, is the exponent of the biggest radius we can fit inside, or sort of fit around the words of length n. Yeah, I think this is the way to think about optimality, because again, we're in a circle. We're going to think about this. I'll pull up one of the pictures because I want to draw a bad circle. Like one of these. Again, we've marked off those intervals because this is literally, S upper n, where S is a set pi, right? We're asking what is the biggest interval that fits inside this manifold. Here, our manifold is 1 dimensional, but the biggest interval is this red one. And so it is actually also of size, best case, we can still find one of size 1 over n. And that is exactly what the main theorem is saying, because sort of yeah, something like this is saying, well, for large m, we're actually going to have m c theta m is rho. And if we just sort of push it onto the other side, this is going to be about over m. And so we get m to the first. And so our covariant exponent is exactly what we. So it's actually kind of amazing that with the Golden Gates in SU2, you can get a covariant exponent bigger than 1, right? That we can actually do better than linear, or 1 over linear. We can do, maybe not quite quadratic, but we know that we have sort of, worst case, it's only n to the 4/3. That's still kind of a miracle. That's better than the linear that we get from the circles. So, hopefully, does that clarify properly?
Okay, good. Thanks. So I'm just going to sneak out and grab some pizza. Yeah. So now the question is, do we want to have it here or do we want to have it downstairs? Yeah, we have it downstairs. So I'll go grab some pizza. And I'll have some. You know what I've sort of realized now too? I did this. Is actually, I think it's, in a sense, it's the key real. It's,
You mean this?
yeah. The Hardy, right? The Slater solution. Yeah.
It is. It's the engine that makes it.
It's the engine that makes it symbol. Yeah.
I haven't actually, I don't know if I've looked at the original paper or if I have. It was a long time ago. It's possible. It's also only in Hungarian.